All right, my friends, let's see how it went. So the first partial sum would just be the 1 there. And so the second partial sum would be 1 plus 3, which you could simplify to be 4. The third partial sum would be 1 plus 3 plus 5, which you could simplify to be, what is that, 9? Okay. Fourth partial sum, you'd add in the 7, so it's 1 plus 3 plus 5 plus 7, which would be 16. Fifth partial sum would be 1 plus 3 plus 5 plus 7 plus 9 would have been next, and then that would equal 25. Okay, so I was hoping that some people think of it as laziness. Some people think of it as, being efficient. But I was hoping that when I asked you for the 12th partial sum, you would basically start to not want to do it term by term, because that's kind of a bummer. And so, yes, it is equal to 1 plus 3 plus 5. And then what would the 12th term have been? I would just go up here to the way they had the terms defined and then put 12 in for n. So 2 times 12 minus 1, that would have been 23. Okay, so I didn't want to write all the terms down, but that's what it would have been term by term. But anyway, I was hoping that you may have noticed that the way our answers looked as we subtotaled it, we ended up, in this case, just getting all these pretty little perfect squares. Isn't that cute? And so, and then you could notice there's a relationship between the number of terms you were adding and the base. So I was hoping that you would kind of say, I think it's probably 12 squared. And so I think it would have added up to 144. And so, and then, which would be, I think, a pretty valid conjecture to have. Have we proved it? No. But, it's a pretty good guess. Anyway, and so what are we conjecturing the sum of the first n terms would be? Well, term by term, it would be 1 plus 3 plus 5 plus all the way up to, how did they define it? Yeah, 2n minus 1. And then it looks like we're pretty much guessing that it would just equal n squared. There we go. All right. And it's this kind of claim right here, in particular, this equal sign right here, this is the kind of thing that we're going to be proving, that that instead of doing certain things term by term, you could use an extrinsic formula, like in this case, n squared. And so this is the kind of thing that we're going to prove. And there are different ways, different methods of proof. And just a comment before we talk about that, in math is different than the other disciplines. In math, if you're given a formula or a theorem or a corollary or a postulate or anything that's been published in the math world, it has been proved. You can lean on it. It's not a guess. It has been proved. And so that's the difference between math and the other disciplines, and in science, oftentimes we'll have tests and we'll say, well, the results indicate, that this is most likely true, right? But in math, if we give you a formula, there's no guesswork. There's no likelihood that it wouldn't work, if that makes sense. So basically, at this point, I wouldn't say that we've proved it. I'd say that, based on the pattern, it looks like it's probably true, but we haven't proved it. And there are different methods of proof. And my favorite is stuff that we did like in chapter 5, where it's like a verify the identity style proof. I like those. They're clean and neat, and for me, easy to read and follow, and they're the easiest to do. And then the style of proof that we would use for a claim like what you see here in the bubble, we would probably lean on a proof by mathematical induction. So let's talk about the theory behind mathematical induction. So the theory behind mathematical induction, it can be explained kind of using a ladder analogy. And so there's two common analogies. There's the ladder one, and then there's a domino effect one. And so personally, I relate to the latter one a little bit more. And so, okay. So let's say that I have a ladder, and this ladder is really tall. As a matter of fact, it has infinitely many rungs on it. So the sucker just keeps going. And let's say that I want to prove that I can climb the whole thing. So how could I prove that I could climb the whole thing? And just a comment here, the ladder is basically representative of a formula here, like what you see here in the bubble, where we would be trying to prove that it's true for all n from the natural number set. So that would mean starting at 1 to 2 to 3 to so on. And so you have infinitely many cases, basically, that we're trying to prove. And you don't want to do it case by case, right? So just like with the ladder, if it's got infinitely many rungs on it and I want to prove that I can climb it, I don't want to have to do it case by case, because not only would it be time consuming, but it would take my entire life, and then I'd have to pass it on to my kids, and they would have to pass it on to their kids, because it's infinite, right? It would take forever. So there's no way that you can prove that you can climb the infinite ladder doing it case by case. So mathematical induction is a way for you to prove something that's infinite without having to do it case by case, since after all, case by case would be impossible. So let's talk about how could I prove that I could climb this ladder. So let's say that that I can prove that I can get my foot on the first rung of the ladder. So that would be like claiming that would be like showing that your claim is true when n is 1. So let's say I can show you, like, I can get my foot on the first rung of the ladder. Well, I think you would say, you know what, that you didn't prove that you could climb the whole thing. And I'd say, you're right, I didn't. But let's say that I could show you that if, let me write this off to the side, if my claim is true for n equaling k, so if the claim is true for n equaling k, where k is some arbitrary constant. So it's some natural number. It's a fixed natural number. I'm just not saying which one it is. So let's say I can say that if my claim is true for n equals k, then my claim is also true for n equaling k plus 1. So let's say I could show you this as well. Then what did I just prove? Since k was an arbitrary constant and I didn't say which one, then, and I showed you that my claim is true when n is 1, then that would mean that if n was 1, then if I've created this loop right here, then if n equals 1 is true, then by creating this loop, that would mean that n equaling 1 plus 1 or n equaling 2 also works. And if 2 works, then 3 works. And if 3 works, then 4 works. And if 4 works, then 5 works. And so I've created kind of this domino effect just by creating this loop right here. So that's what mathematical induction looks like. You have what's called a basis step, and that's the easiest part, where you just show that your claim is true when n equals 1. And then you have what's called this, where you create this loop right here. You have what this is called your inductive step. And what you do is you assume that your claim is true for n equaling some arbitrary constant. And then using that assumption, the burden of proof is showing that then that would imply that your claim is also true for n equaling that constant plus 1. And by doing that, you created a loop that would generate the entire sequence, that would generate the entire claim, essentially, for any n value. Okay. And this is the part that I always have the hardest time explaining, but I think it's time to probably just go into an example and show you what it looks like when we do this. So we're going to start by doing this using an outline, and then we'll show you what this looks like when you try to do this in a paragraph proof style. So first, let's do the outline. So, okay. So let's say for part B, we're asked to prove that S sub n equals 1 plus 3 plus 5 plus 7 all the way up to 2n minus 1. We're trying to prove this little equal sign right here, that you could do this just by squaring n instead. And we want to prove that it's true for every natural number ever, okay? So basically for the outline, all you have to do is you have to show that your claim is true for n equaling 1. So this is the basis step, which is show that the claim is true when n equals 1. Okay, and I'll leave a little bit of space for you to do that. And then we're going to do the inductive step. And the inductive step is where you basically say that we're going to assume that the claim is true for some k value. Let's see, or so for n equaling k. And actually, let's just say like where k is an arbitrary constant. Okay, and I'll leave some space for us to show what that would look like. And then once you make that assumption, then what you have to do, so the inductive step is using this assumption, then you have to show that, say, using your assumption, the claim is also true for n equaling k plus 1. And we'll leave, that's where this is where most of the work is in this last part. Okay. All right, my friends, between now and the next video, I want you maybe just with super light pencil, just in case you mess it all up. It's always easy to erase. Go ahead and see if you can, in these little gaps that I've left, so like here, here, and here, see if you can just play with it. Don't be afraid to be wrong. Just kind of play with it a little bit. And then you can check in with me in the next video and I'll go through these parts with you.